Welcome viewers to the 11th lecture of our online course on non-traditional abrasive machining methods, and today we are going to start with abrasive jet machining or AJM. What is abrasive jet machining? Abrasive jet machining is in which there is a nozzle through which abrasive particles, that means abrasive grits, are carried in a high velocity gas stream to impinge on a workpiece surface and remove material by impacts. Why is the material removed? Because whenever essentially brittle materials are generally preferred as the work material in these cases. That means, if we have brittle materials, abrasive jet machining which will be very much usefully applicable. So, if we have a brittle material impacted by such abrasives, what are these abrasives? They are generally some particular metallic ceramics which have very high, not only metallic, but they can be ceramics in general, which have very high hardness, essentially high rigidity, and they have high melting temperature also. But main thing is that they have very high hardness and they have very high form stability, and therefore, when they hit the workpiece surface, they generally cause fractures due to impact. And when these fractures accumulate, they are going to produce damage, which we refer to as material removal, and we can create grooves and cuts, etc., or drills, holes, etc., by this method in such hard, brittle and non-conductive materials, conductive also, but for conductive materials there are other competing processes, but for hard, brittle, non-conducting materials, this process is almost without any competition, these processes. So, let us have a quick look up at the method. How is material removed? By impact erosion of work material with abrasive grits at the speeds of 150 to 300 meters per second. Some people even consider it to be 100 to 300 meters per second. How are abrasive particles accelerated to velocity range? This is by a gaseous medium at high speed. What are the typical abrasives used? The typical abrasives used are aluminum oxide, silicon carbide, glass beads, etc. What is the typical size range? They are in the size range of 10 to 50 microns. What are the typical applications of this process? It can be used for cutting, drilling, micro machining of brittle non-conducting materials like glass, ceramics, semiconductors, composites, heat sensitive fragile materials, etc., etc. How is material removed? Let us have a quick look. So, this is the abrasive and this is the work material. Just one such abrasive is being shown, and it goes and impacts the work material, and we are conversant with this particular geometrical figure in which this is what happens, and we have already done this particular calculation. I just remind you what we are talking about. This is the abrasive grit which has hit the workpiece material, and this dotted line shows the line of fracture by virtue of which a hemispherical chunk of material is getting removed. The relation that we had derived was that delta being the indentation and large D being the diameter of the damaged circular portion at the top of the damaged crater. Okay, if this is the diameter, and if the diameter of the abrasive grit be D, In that case, we can have Pythagoras relation. Just one moment. Yeah, we can have, I will just draw a quick figure to show you what I am talking about. If you look at it here, this is d by 2, this is d by 2, and this is d by 2 minus delta. So, this square plus this square must be equal to this square. So, returning back to the figure, we see hypotenuse square is equal to the square of the other two sides, and from here, if we neglect delta square to be too small, we will ultimately arrive at this particular relation. I am not doing this relation, I am sure you can do it. So, d will be equal to 2 into root over d multiplied by delta. This we have already done before, it is done in all books, textbooks, etc., and you also can very easily derive it. So, let us proceed. What we see is that a grit is coming and hitting the workpiece surface, and the grit is, mind you, at very high speeds. So, what we say is that when it hits the workpiece surface, how does the material get removed? And here we assume that the complete kinetic energy of the grit is converted into plastic strain energy of the work material. So, if the work material is plastically deformed, the work done, which is due to this plastic straining, can be expressed as half into F into delta, where F is the maximum force of plastic deformation which is occurring, and delta is the indentation due to plastic deformation. Since maximum force is not existing all the time, so we take half of it as the average over the particular time of deformation. So, we have the energy carried by the abrasive particle being half mv square, where m is the mass of the abrasive grit and v is the velocity of the abrasive grit. So, half mv square must be equal to half into F delta. Okay. Force into displacement is equal to work done, and here the mean force of half F has been considered. So, with this expression we will have m into v square is equal to F into delta. Now, if we break down mass and write it as density into volume, we can quickly write, considering that assuming that the abrasive grit is a perfect sphere of diameter d, we can write half into density into volume 4 by 3 pi r square equal to pi by 6 into d cube multiplied by velocity square. You will say, what is the value of the velocity? I will say, I do not know, whatever velocity has been set, I do not know it. So, I am using a variable value equal to half into the projected area of of the contact of the abrasive particle with the workpiece in the ultimate situation, projected area. So, how much is the projected area? The contact area, okay, its projection on the xy plane. So, that is why we have written pi by 4 into d square, d being large d, multiplied by stress. Now, why are we doing this? We are saying that since plastic deformation is taking place, the force which is existing, the maximum force which is existing and thus creating the ultimate crater, it must be equal to the flow stress of the workpiece equal to sigma w multiplied by the projected area. So, that is why we are replacing maximum force by the plastic flow stress multiplied by the projected area, and delta was already there once. And we are interchangeably using flow stress of the workpiece material with the hardness of the workpiece material. They mean the same things to us. Now, if we simplify this and find out, we will find that this gives us a relation like that. Let's have a quick look how we process this. So, we can write half into rho into pi d cube divided by 6 into v square equal to half into pi d square divided by 4 into sigma w into delta. Here you will notice I can scratch this out, this goes away as well, and what else? This will be 3 and this one is 2, and therefore I can write delta equal to, that is starting from here, delta equal to this one goes down. So, I can write h instead of sigma w, this one remains here sigma rho. Okay. And what else was there? Oh, I had 3 here, by 3 multiplied by 2. Okay. What else? Let's see if v square was here, v square. Now comes d square. Now, what is d square going to do? D square will be going and settling down as, oh, this is tricky because it has a delta inside. D square will be equal to 4 d into delta, that means delta square, and therefore we will have we considered, oh, there is one d cube here. So, if one d cube is here and d square 4d, oh, this will cancel and this will become to the power 2. Okay, we have retained d cube and we have cancelled it out, so that delta square becomes, this one cancels, 2, delta square becomes equal to rho by 6h, this 2 goes down, 6h into d square into v square, okay, which means delta can be written as root over rho by 6h into d into v. That's all. So, that's the relation. If we come back to the screen, you will find that's the relation that we were supposed to get. Delta is equal to, that means the indentation is related to d. Larger the grid diameter, more will be the indentation, which is common sense. More will higher the velocity, more will be proportionately high will be the indentation, and of course, it is related to the density and the hardness, density of the abrasive particle and hardness of the work material. Once we have arrived at this particular expression of delta, let us proceed on to find out an expression of MRR. MRR, we know we can express it this way, it is equal to MRR due to one impact, that means material removed due to one impact, multiplied by the number of impacts per second. This should be material removed, not MRR, because the rate is coming here, number of impacts per second. So, material removed due to one impact multiplied by number of impacts per second is equal to MRR. How do we find out the number of impacts per second? What are we given? In the machine, generally we are provided this information, say the abrasive mass flow rate will be provided to us. What kind of values will it have? Say 2 grams per minute, 3 grams per minute, like that. So, that way abrasive mass flow rate, suppose it is m dot. If it is m dot, it means as m dot grams per minute is being used. So, if that be so, how can we find out the number of abrasives present in such a abrasive stream? What we do is, if we come back to the screen, number of impacts per second, if we come back to the screen, have a look at that. Number of impacts per second is equal to mass flow rate of abrasives, that means m dot, divided by mass of one abrasive. Okay. So, that will give me the number of abrasives in that particular stream. That is good. So, numbers, mass flow rate of abrasive divided by volume of one abrasive into density of one abrasive equal to m dot divided by, once again, that 4 by 3 pi r cube that we have expressed in diameter will give us pi by 6 into d cube multiplied by density. So, mass of one abrasive particle is here, it divides the total mass flow rate of abrasives, and therefore, this gives us the number of abrasives in the stream, and if we assume that 100% efficiency is there of impacts, we can say this very term is the number of impacts. Having understood that, let us now quickly calculate this out. How do we calculate it? We say that pi by 12 into d cube. What is pi by 2 into d cube? 12 into d cube? Pi by 12 into d cube happens to be the hemispherical chunk which is removed per impact, multiplied by the number of impacts. I have just copied down the number of impacts which we deduced just now here. That is good. So, what do we have here? We have number of impacts I have kept unchanged. What else is there? This pi will cancel out, this 12 and 6 will leave behind a 2 here. So, there is a 2 here, and d cube I have imported from here directly to write d cube, and rho here also I have directly imported it here, and this d cube which is here, for that I have written 4 into d into delta. Okay. Why? Because this is the expression of square, d square. So, I have taken to the power half, so that I have taken d here now, but d cube is there. So, I have taken it to the power 3. So, first from d square to d is done by this 2, and from d to d cube is done by this particular power. So, this is equal to the intermediate expression between this one and the final answer. So, if we simplify this, since a d to the power 3 is at the bottom and d to the power 3 by 2 is at the top, therefore, they will interact and form d to the power 3 by 2. That is good. And what else? What are the other terms that we have to think about? We have to think about, what about delta here, right? So, delta, we have derived the expression of delta a few minutes back, and I have directly put in the value of delta here. Remember, rho by 6h into d into v. Therefore, what we notice is that we had got already d to the power 3 by 2, and we are getting a d to the power 3 by 2 here, and therefore, this d to the power 3 by 2 cancels out, and the funny thing is the final expression does not have the expression, I mean the contribution from diameter of grit at all. It's extremely interesting, but it's true. The final expression of MRR in abrasive jet machining will not contain any expression of D, that means abrasive grit dia. It is not affected by that. Secondly, what do we have here? We have V to the power 3 by 2. So, out it comes directly V to the power 3 by 2. What about rho? We have contribution of rho from here, which is 3 to the power 3 by 2, and again another root sign. So, it will be 3 by to the power 3 by 4, and here we have rho only. So, naturally at the bottom we will have rho to the power 1/4, 3 to the power 4 on the top, and 1 at the bottom. So, we have rho to the power 1/4. M dot was M dot from the beginning to the end, and thus it remains, and hardness is present here. So, its power is 3, and due to this root by 4, 3 by 4. So, h to the power 3 by 4, and all these constants, they can just be crunched together and found out, and it comes to be 1.04. So, it is so simple. Material removal rate of an abrasive jet machining process can be expressed simply by this particular expression, 1.04 into m dot into v to the power 3 by 2 into rho to the power 1/4 into h to the power 3/4. Okay. So, we will use this expression to solve a number of problems. Let us have a look at them. A researcher is experimentally determining the ratio delta by dg. What is delta by dg? Delta is the indentation depth, and what is dg? dg is the diameter of the grids. So, what you might say, what is it trying to do? The researcher says that for any material, I mean, this is backup information, that is, there should be a y always associated with a particular solution of a problem. If we are trying to solve a problem, we have to first of all see whether it is meaningful to do it, or we are doing something just for fun, or just some abstract academic interest. So, a researcher is experimentally determining a ratio delta by dg. What can it perhaps represent? If it is a soft material, delta will be higher, and if it is a very hard material, delta will be lower, and therefore, you can say that I can measure the hardness this way, or you can say I can give you an estimate how much will it be, will its machinability be when you are considering the case of abrasive jet machining. Okay. So, you will say give me the material, give me the abrasive powder type, that means what diameter the average diameter it has, and give me delta by dg. I will tell you how much machinability this particular material will have. Okay. This is the reason for which he is possibly trying to find out this value. Okay. But so, what is the problem? Let him measure it. But the problem is this: dg is so small that if you fire an abrasive particle towards a source, I mean towards a target, and try to estimate how much damage it has made, it is extremely problematic due to the size effect. Okay. And how do you control essentially one abrasive particle, make it hit, create a damage, etc. So, the general procedure is, if you are really interested in doing something like that, fire an abrasive jet towards towards a target for some time, calculate the number of hits by the method that we have done, and then divide the total cumulative damage by the total number of particles which may have hit the body during that time, and that way find out an average delta by d. But the researcher is not satisfied with this. He will say maybe half the impacts are not taking place, maybe one is hitting on top of the other, and therefore, he is saying that it will not represent the true picture. So, he is planning for a laboratory level experiment, where he will say I will get a very accurate picture of what is going on. Okay, that is good. So, what he has done is, he is selecting the case of abrasive silicon grids with density 3.2 grams per cc, diameter 50 microns, and the material to be glass with hardness of 2660 newtons per millimeter square, with abrasive velocity equal to 200 meters per second and jet diameter d equal to 2 millimeters. But he is not doing the experiment with this one. He is doing the experiment with a scaled up model where he is using a tungsten carbide ball with a density of 15.8 grams per cc, and the diameter of the ball is 5 millimeters. So, instead of 50 microns, which can hardly be seen by the naked eye, he is using 5 millimeter diameter. 5 millimeter diameter tungsten carbide ball. And what is he doing? He is taking as the work material a glass with hardness 2500 newtons per millimeter square. So, he will drop this ball, and this single ball will cause a damage of significant dimensions which he can measure. So, he is saying I will do this experiment with a single ball and get a very accurate representation of indentation at the lab level, okay, on large workpiece. I can measure it and get an estimate. There will be no overlapping of results of a number of grids in this case. So, that is a quite well planned experiment, but the problem is, for proper simulation of the actual situation, what should be the velocity imparted to the ball to impact the glass surface in the scaled up experiment? Now, what does that mean? It means that everything is different. The diameter of the ball is different, the density of the ball is different. Instead of density to be 3.2 grams per cc, it is 15.8 grams per cc. Instead of diameter 50 microns, it is 5 microns, 5 millimeters, much higher, and the glass also is, instead of 2660, it is equal to 2500. So, how can we possibly simulate? The answer to this is, since he is finding out delta by dg, okay, he is trying to find out delta by dg, mind you. In that case, let us see what value the velocity should have, so that delta by dg comes out the same in both cases. Okay. I will take such a velocity such that the delta by dg will come out to be the same in the theoretical case as well as the experimental case. Delta by dg, delta 1 by dg1 should be equal to delta 2 by dg2. We know that delta by dg is equal to rho by 6h into v. This d is simply taken to this side. So, if this is the expression for delta by dg, let us put the values of the first case here and the second case here and say that if they are equal, what should be V2? Okay. So, rho 1 in case of the first case is 3.2 grams per cc. Just one moment. Rho 1 is 3.2 grams per cc by 6h. H is equal to 2500. Just a moment. Am I correct in this one? The values. The first case, the hardness is 2660 newtons per meter square. Friends, this will be 2660, okay, and this is 200, the initial velocity, and this is 15.8 by 6 into 2500, it should be equal to V2. Shall we try out in Excel quickly? That's a good idea. Okay, let's do that. I'll quickly get an Excel working. Just hold on. That's it. Let's first derive what we have written. please have a look here first. So, we have rho by 6h root over into V. This one is the expression of delta by dg. So, this will be 3.2 divided by 6 into 2660 root over multiplied by 200 equal to root over 15.8 divided by 6 into 2500 into V. Let us do some cancellation. This goes out, and therefore, V will be equal to 200 multiplied by root over 3.2 by 15.8 multiplied by 2500 into 2660. Let us solve this. So, we have equal to 200 multiplied by square root of bracket. Let us take another bracket for the numerator. What is the numerator? It is 3.2 multiplied by 2500. Is that correct? Yes. Divided by bracket 15.8 multiplied by 2660, bracket closed. Okay, it seems to be all right. Let's press it and get the answer. Now, what's that? You must have left some bracket. Okay, they are giving an answer of, let's recheck it. What have they done? Oh, they have given a bracket here. That's good. Okay, square root. So, the answer is this way. Velocity comes out to be 87.25. Okay, 87.25. If we come back here and have a look at the previous at the problem that we were discussing, this was 87.5. Okay. So, this is the answer. If you drop this ball with a velocity of 87.5 meters per second on the experimental glass, in that case the delta by dg that we will obtain experimentally will be exactly equal to the delta by dg in the theoretical case, and that way in a scaled up experiment we will be able to estimate delta by dg. Last of all, if you drop it from a particular height, what should be this height? 380 meters. So, if you drop it from 380 meters, it will develop 87.5 meters per second. Okay? I hope this was easy to understand, not very difficult and interesting also. So, next day we will continue with this discussion. Thank you very much.